Hey everybody, it's me, Steve. This is going to be the second part of the mineral identification of what I suspect is some sort of nepheline, monzocyanite, something like that. And I am going to talk about the subsequent tests I've done. I still think the rock is. I have not actually classified it yet. I have not put it on the FAP part of the QAPF diagram. And I'm just going to do that. At the very end here, I need to normalize to do that. So I'm going to, post it here at the end. So I still think it's either for nepheline monzocyanite or a nepheline monzodiorite, probably on the cyanide side. But I came to a couple revelations with this. When I was running early this morning, I was running the tests. And I streaked the minerals. The white ones, there's actually 3 white ones, not 2. There's 3 white ones, and the red one all streaked white, which is typical of plagioclase and case bars, nothing out of the ordinary. But that black streaked. It's streaked. Well, I called it hornblende. I still think there's augite in there. The greenish black is still augite. But hornblende doesn't streak black. I was like, okay, that's odd. So I scratched it. It's scratched with the number 5, which hornblende can scratch with the number 5, but it isn't typical. It's more with the number 6. It scratches deep. It's okay. It's like, all right, I ruled out biotite. There is now no biotite. It's not that. I'm like, okay. So I'm like, what else? I'm like, well, it's got to be an iron mineral. I should have gone with my instinct. When I originally, in the first video, when I say it looks metallic, it's because it is metallic. I should have gone from there. And if you look in some of the, under magnification, you'll see the black metallic minerals actually within the feldspars. So it kind of formed late. It was probably actually formed secondary, kind of like the fluorite probably did. Usually they get fluorite and igneous rocks like this through hydrothermal activity. So that clued me into something else. Now that I suspected I might have some hydrothermal activity affecting the rock, I'm like, it looks metallic, it scratches with the number 5, it streaks black. I'm not wondering if it's hematite. Well, I'm looking a little closer. The crystal structure, there are some crystals in it. I was correct, but the crystal habit fooled me. It led me to identify it tentatively as hornblende, but that's why we have other tests. See, I'm not infallible. I said this before. But I'm like, I'm going to try something. So I took my weak magnet that came with my hardness picks, and I tossed it on there, and it sticks. I mean, hard sticks. Which, that magnet's not very strong. It should, if there's just a little bit of magnetite in there, it should fall off. Well, it didn't. So that black mineral, what I thought was hornblende, is magnetite. And like I said, I still think that the clinopyroxene augite is still in there at the percentage I thought it was. So I was wrong on that one. I caught the mistake. That's why we have other tests, and that's magnetite, not hornblende. So I said there are 3 white minerals. First of all, I just want to say, after doing the acid test, there's no carbonates in this. The weak 3 to 5% acid didn't fizz. The 10 to 15% acid didn't fizz. Matter of fact, I had to restock the acids this morning, and they've been sitting on the shelf for about a year. I should have done that anyway. But you put the 10 to 15% on there, and you do get that cloudiness on the rock. It's hard to see. I tried to record it. You couldn't see it through the camera on the smartphone here, but you could see it with your eyes, and the 3 to 5% didn't do, and there's no reaction. So there is nepheline. However, after doing that test, the nepheline is in a lower percentage than I thought it was, and there is this 2 to 3% other whitish mineral, slightly yellowish, tintish gray, maybe a little. It's hard to describe the color because it changes when you look at it under magnification. It looks, other than the color, it has that granular texture to it that the case bar has, that the anorthoclase has. So it probably is a case bar. It's just very light colored. This happens it's nothing out of the ordinary. I scratched it. The scratch test leads me to think it is some other case spar or a white version of anorthoclase. It's no big deal. So we have a little more case spar than I thought, but we also have a lot more plagioclase than I thought. So I need to readjust the percents, and I will do that. And at the end of the video here, I will do the actual rock classification for you. Okay, so after I did the subsequent lab tests, I'm just going to go through this kind of quickly because there's math involved and I don't want to bore you to death. But the percentages I got are basically here. What we have is our sodalite and nepheline together. We need to combine those to do this normalization. Since they're both voids, 23.5%. Now we have our 3 feldspars, actually. We have 1 plag, 2 case spars. We need to combine the case spars because on the FAP plot, we keep the plagioclase separate from the case spar. So our case spar is, which is going to equal our A, alkali feldspar. That's where it comes from. F is void on the diagram, A is alkali or case spar, and P is plagioclase. We get 29%. Our plagioclase, which is case is probably oligoclase, is 37%. Now, our mafics and our secondary minerals, I've added them all up here, 10.5%. We are going to exclude them from the normalization because they are not part of the plot. Now I've added together my mafics, which is my M, my secondary, which is my S, and that totals 10.5%. That needs to be removed from the FAP plot because it's not on there. That's why we normalize. We actually normalize twice to plot this thing. So we aren't going to exclude them in the naming because magnetite is significant. I'll get to that at the end. So we were just dealing with our voids, our alkali or case spars, and our plagioclase. Okay, those are the 3 things we're dealing with when we are doing this normalization. So here, looking at the card really quick, you can see that after we remove our M's and our S's, our mafics and secondaries, we're left with 89.5% of the rock. We normalize for voids first because those are plotted first. I've done this before, so I'm not going to go through the details of it for you. And we get 26.26%. We normalize our case bar and our plagioclase there, and then we check it to see if they add up to 100. They do. Okay, good. We move along. That 26.26 is going to be our plot for voids. Now we have to normalize our case bar and our plagioclase. So we follow the same process, except now we're dealing with 73.74 as our total, not 89.5, because we've already excluded the voids. Okay, so first you have to remove any mafic secondaries. You pull those out, and then you normalize for your voids, and then once your voids are done, you pull that out, then you normalize your alkali feldspars and your plagioclase. We check again, we get 100%. So now you're done normalizing. We have voids at 26.26, case spar, alkali feldspar 43.94, and plagioclase at 56.06%. Now, those don't have to add up to 100. We checked them as we were going. And the reason why I checked them is because I'm only rounding. When I was doing the initial additions that I would divide by 100, I'm only carried that to 4 decimal places. You should do that, like the 1.1173 that you saw, that kind of thing. And then carry it to 2 decimal places when you run it through, and then you can, at the very, very end, round those 3 numbers to whole decimal places if you want. Instead of 26.26, it'd be 26, and then 44 and 56. Because the plot, it's a manual plot. I'm going to do here. So anyway, we're using the bottom half of the QAPF diagram, the FAP part, the FAP part, I've said this before, and it plots as a void Monzo diorite. However, I am giving the rock name as a nepheline Monzo diorite with magnetite. Why am I doing that? Well, because you can use modifiers. I already explained in the last video that the word void on the FAP part can be substituted with the dominant void if you have a clear dominant void, and we clearly do. But I added the with magnetite because magnetite is not a part. The mafics and secondary minerals do not go into the QAPF plot at all. So if they're significant, like in this case, we have magnetite at 8.25%. That's a lot. So this is not a set in stone thing I'm about to tell you. This is my general guidelines. When I'm classifying igneous rocks like this, if I have less than 5% of a mafic or an accessory, or the total of the twos, I just leave it out. There's no need to mention it in the name. 5 to 10%, we get the suffix with /XXX, in this case with magnetite, because we have 8 1/4 that falls in between 5 and 10%. 10 to 45%, you put it in the prefix. Like if it was, like, say we had 20% magnetite as a secondary, in this case, I would have a hematitic nepheline monzodiorite. That's what I would call it if I had like 20% hematite. Or if I had 20% magnetite, it'd be a magnetitic nepheline monzodiorite. Okay, something like that. And if you have 45 to 55%, it's an and, because it's considered borderline. You give it two names anyway. So that's just a general rule I follow. Some of those percentages might vary a little bit depending on how significant I think, it is, the accessories or the mafics are. So in quick summary, what we've learned and I've learned here is that when you have voids, in an igneous rock and a rock in a box. This rock, like I said, I probably pulled off the shore of Lake Superior and then forgot I had done it and set it aside because it would look cool and to run tests. But anyway, it's a rock in a box. This is why, and I keep saying this and no one keeps listening because I keep getting pictures of stuff like this. This is why we don't identify rocks from pictures, especially when there's no context associated with them, and especially with no scale. Because this was difficult enough, and I have the tools to do it. All right? So, anyone looking at this rock, I would say if you just toss at me and be like, that's granitic, I wouldn't say that's a granite. But most people just looking at that would probably say it's a granite. And a lot of geologists would probably say that, and it's not a granite at all. See, so you've got to take into account the fact that this is not an easy looking at everyday objects. You have some change in your pocket, and I don't even know if I do. But no, I don't. If I did and tossed some change on here, you can tell the nickels and the quarters and the dimes, because everyday experience, it's man-made stuff. The natural world is not that simple to figure out. And if you get anything out of any of these videos, I want you to get that out of them, that the natural world is hard to classify and categorize so we can understand it. We do these things, QAPF diagrams, all this stuff, so we can talk about it and we can understand it. It's for us. It doesn't necessarily mean the natural world is reflected in our constructs of it. The natural world is not subject to our rules of logic or our preconceived notions of it. Other than that, the big picture learning, we have voids, so we can't have quartz. We have to use the FAP part or the FAP part of the QAPF diagram. We have learned, and I have learned, that sometimes just looking at a mineral under magnification isn't enough, because like I said, the crystal habit on that magnetite kind of fooled me a little bit. But there were other key indicators that should have told me it wasn't hornblende. But I screwed up. It happens. We learned that the other tests can help. So that street test led me to a scratch test, which kind of suggested it was soft. A lot of soft metal minerals, metallic oxides like a magnetite is, hematite, things like that, are a little softer than, typical minerals hardness of 6. A little bit. They can be 6, but they're generally less. After I did that, I got the idea of sticking a magnet to it. I would have gone with hematite if the magnet didn't stick to it, but the magnet stuck to it hard. And so it's magnetite. There's no hematite in it. It's all magnetite. And the fluorite should have also keyed me in that that was not hornblende, that I probably had an iron, some sort of iron oxide, some ferrous mineral in there, because fluorite in igneous rocks is generally an indicator of hydrothermal activity, and iron minerals tend to be brought up in hydrothermal activity. So, you know, I found the error and I fixed it. All right, so then once that was done, we did our total percentages, and I already went through this with you, so we could classify the rock, give it a rock name. We use the QAPF chart. Once again, I'm going to keep beating that horse because it's so important classifying igneous rocks in general, in this case a phaneritic or coarse-grained rock. You know, some people might say the QAPF diagram for granitic rocks is a plutonic chart. I try not to say that. I still do, because plutonic indicates an origin. We have been moving away the past 30 years from classifying rocks based on origin. We've been moving to, you know, basically identifying rocks and rock units based on their lithologies, which is the way it should be anyway, because that's how we categorize formations in other formal units like lithoderms, stuff like that, igneous suites and stuff. We use the rock lithology. So you'll see things like till and the rock form tillite have lost favor. I still use them too for diamictin, diamictite, which also includes things like debris flows. So we're getting away from the origin. So technically, the QAPF diagram for coarse-grained or phaneritic igneous rocks is what we were using. There is an aphanitic or fine-grained igneous rocks. So anyway, I think I'm going to wrap it up here. I don't want this to get too long. But anyway, if you have any questions or comments, please leave them below, and I hope you learned something.